Hello and welcome to this video lesson. Here we will be doing some practice questions on net force and first law of motion. I have taken this exercise from Chris Meyer from one of his notes in 2014. It's a fantastic exercise, probably one of my all-time favorites. And we are going to complete this table. So for each force diagram, decide if the forces appear to be balanced or unbalanced. Write the expression for the net force in the x and y directions. Use the direction right or up as positive. What is the resulting motion? Is it accelerating, or is it at rest, or is it at constant velocity? Look at the sample answers for hints on what to do. So there's a few sample answers here for each one to kind of get you an idea about how to start this. All right, I'm going to bring this up and I am going to write our positive direction. So positive and positive. This is what we said we want our positive to be based on the question. And we're going to look at the first situation here. We have two forces acting. We got force of friction and force of, or applied force acting in the left direction. So we can see that this one is a lot larger than this one, and therefore they're unbalanced. And the net x, force in the x direction, is going to be this minus this. And the motion here, since it's unbalanced, it's going to be accelerating. And if it's accelerating also in terms of direction, it will accelerate towards the direction that has the larger force. So we'll talk about this in more detail later, but accelerating to the right. For our next one, we got two forces. We can see that they're unbalanced because this force is bigger than this one. In terms of net x, we're taking right to be positive, so we're going to take the positive force. This one is going to be positive and this one is going to be negative. So when we add a positive to a negative, it becomes force of, that looks like a T. It's a little bit hard to read. So that's Ft minus Fa. So again, positive and negative. And these are vector sums, so when you add them, it's kind of like this is positive and this is negative, so you're always adding everything here. Okay, in terms of acceleration or motion in general, unbalanced, it means that there is going to be acceleration. In which direction? In the direction that the force is bigger. In this case, the direction left. For the next one, these two forces, we can see that they are the same, so they're balanced. The net x force is going to equal to the force going in the right minus the one to the left. And since they're the same magnitude or balance, it's going to equal to 0. And the motion, whenever there is no net force acting in a certain direction, it's either at rest or constant velocity. If it's at rest, it's not moving. Constant velocity, we don't know if it's going to the right or left. We need to be given the initial information about the object if we need to know the direction. But for now, we do know that it's for sure either at rest or it's moving at a constant velocity. Okay, for this one over here, we got two forces acting in this direction and one acting in this direction. The magnitude to the right is a lot more than the one to the left, so this is for sure unbalanced. And the net x, I'm going to take all the ones to the right as positive, plus f of t, minus the one that's going on the left. And this is accelerating in the positive direction, or to the right in this case. Okay, that was our first one. For our second one, we have everything is kind of the same. It's just in the vertical direction, and we've taken up to be positive. So the first one is balanced because these two forces have the same magnitude. F net y, because I've taken up to be positive, then everything going up, I'm going to treat them as positive, and everything going down, I'm going to treat them as negative. And the motion here, since it's balanced, and these two are going to equal to 0, if the net force is 0, that means that based on the first law of motion, the object is either at rest or at a constant velocity. For the next one, is it balanced? Well, we can see that the normal force is acting upwards, gravitational acting downwards. This is bigger, so that means it's unbalanced. Forces up is positive, so this subtracted by this, and it's unbalanced, so that means there for sure is going to be an acceleration, and it's going to be in the direction that has a larger force. This is downwards, or you can kind of think about it in terms of accelerating in the negative direction. Okay, for the next one, is it balanced or not? Well, the magnitude here and here, when you see the addition of these two, are the same. So I'm going to say that these are balanced. And in terms of forces, everything in the positive direction, I'm going to treat them as positive values, and everything in the negative direction, I'm going to treat them as negatives. And since they're balanced, they're going to equal to 0. And our motion is going to be either at rest or constant velocity based on first law of motion. Whenever the net external force acting in a certain direction is 0, the object is either at rest or constant velocity in that direction. For my next one, I got applied force up, Fg down. This is a lot bigger, so this is unbalanced. And F net y is going to equal to the force acting upwards, positive, and the one downwards is negative, and negative acceleration or acceleration in the downward direction. Okay, let's move on to the next question. We got two forces acting in opposite directions on an object. Force to the right, or Fr is to the right and Fl is to the left, indicate the direction of the acceleration with a wiggly acceleration vector. Compare the size of the two forces and draw a force diagram. Okay, this is beautiful. We can do this. We have a motion diagram. Our diagram starts from position 1, it goes to 2. So the acceleration here, because we can see that the spacing between all of these are the same, so it means that we have no acceleration, so acceleration is going to be 0. Compare the two forces. Well, if the acceleration is 0, if it's going at a constant velocity, that means the forces are equal. So Fl, in terms of magnitude, is going to equal to Fr. So you can see that the magnitude of the two forces are actually the same. And this is the force diagram for it. For the next one, we can see that the force in the left is bigger than the force to the right. And if that's the case, that means it for sure is going to accelerate in the direction where the force is bigger. So that's going to be in this direction. And the force diagram, we know that Fl is bigger and Fr is smaller. So in my case, I'm just drawing, I'm not putting the vector sign. This just means the magnitude of Fr, and this is the magnitude of the force in the left direction. And we can see that this object is starting at position 1 and going to 2, and its acceleration is in this direction. And since motion is also in this direction, it means that it's speeding up, and we can see that it's speeding up since the spacing are getting bigger and bigger. In this situation, from position 1 to 2, the object is going in this direction. We can see that it's speeding up, and since motion and speed are in the same direction, then that means that it needs to be accelerating in that direction as well, because whenever the direction of acceleration and motion are the same, it will speed up. In terms of which force is bigger, if it's accelerating in this direction, that means Fr is going to be bigger than Fl. And that means in our force diagram, the force in the right direction is going to have a much bigger magnitude than the force in the left direction. Okay, for this one now, we are starting from here and moving in this direction, so we can see that our motion is to the left. We can see that in terms of our speed, we're slowing down because the spacing here is getting smaller. So if we're slowing down and moving in this direction, that means our acceleration needs to be in the opposite direction, because in order to slow down, the direction of motion and acceleration need to be opposite, and that's something we learned in the previous unit. And if acceleration is in this direction, that means Fr is bigger than Fl, and in terms of our forces, Fr has a bigger magnitude than Fl. Note that another way of thinking about this is if the object is going in this direction, that means if something is pushing it backwards, which in this case, this force is bigger than this one, so something is pushing it backwards, and that's causing it to slow down and resist the motion. Okay, in the next question, we have each situation is described by a force diagram and an initial velocity. Draw a motion diagram for each situation. You may assume that the object does not change its direction. Okay, we can see for the first one that the force of friction is bigger than the force of tension. It's saying initial velocity is 0, so that means at point 1, I'm going to assume that point 1 is here. Initial velocity is 0, so if this force is bigger, that means that from 0 it's going to start accelerating in this direction and move in this direction and speed up in this direction as well. So our motion diagram needs to be in a sense that it's accelerating, or sorry, it's speeding up, and in this case you can see that the spacing is getting bigger and it's speeding up. Okay, in our next diagram here, we have our initial situation. It's saying that it's moving in the negative direction. So that means initially it's here, and then it's going to end up here because it's moving in the negative direction. Velocity is in this direction. Force, this force is bigger than this one, meaning that the object is accelerating in this direction. And since it's moving in this direction and accelerating in this direction, then it needs to be speeding up. So that means the spacing here needs to get bigger and bigger. In the next situation, we have our two forces. This one is bigger than this one, but in terms of our motion, we start here and we end up here. So that means our motion needs to be in the positive direction. And let's make sure it makes sense. It's moving in this direction. Its force in this direction is bigger, meaning it's accelerating in the opposite direction. And if the direction of motion and acceleration are opposite, it needs to slow down, and in this case it is slowing down because the spacing from 1 to 2 is getting smaller and smaller. Finally, for this diagram, we have the two forces. They're balanced, and if they're balanced, that means the object is not accelerating. Its initial velocity, sorry, its direction of velocity is positive. That means it's starting here and moving in the positive direction. And since these two forces are the same, that means that it's not accelerating, and that would mean that the spacing between the points need to be consistent or constant. So I'm just going to draw it like this and just assume that those spacing are the same. All right, we have one other question for this homework or this practice, and this is saying use the first law of motion to justify why headrests were built. Well, let's see. Let's say you're sitting in a car and your body looks like this, and you got your chair. I'm going to draw that with red. Looks like this, and you got your legs there. Okay, so what ends up happening is as soon as the car starts to move, especially if it's moving at a very fast rate, then there's going to be a force acting on the back of your body. And that force is going to push your body in that direction. Note that basically all of your back, your feet, and even this part of your feet usually is kind of like landing on the ground, so there's some frictional force acting on it. So as soon as you get pushed, there's going to be a net external force acting on your back, which pushes in this direction. Now, your head here, there's nothing pushing that one. And based on first law of motion, if there's net external force acting on your body, then it's going to be accelerating. But if there's no net external force acting on your head here, then it's not going to be accelerating. So what's going to happen a moment later is that your body is going to move with the car because it's accelerating in that direction. But your head is going to stay where it was a minute ago. And that's going to cause your head to kind of to extend like this. And it could cause a whiplash injury. So you're going to get all your neck muscles extended, maybe more than they need to, especially if you're accelerating much faster. This part of your body will move fast and this part will not move, and therefore you can cause severe injuries. So that's why car seats started having headrests. And obviously, this is very, very important because now as your car starts moving or accelerating, the body will move, and that's going to cause a force on your back. But as the car is moving, the same force is going to be applied to the rest of your body as well. So usually a body which is in motion will stay in motion unless there's a net external force acting on it, or an object that's at rest will stay at rest unless there's a net external force acting on it. So if there's nothing acting on it, it will stay the same. The rest of your body will move and you will get an injury. But if you have a headrest, net external force acts on both of them will move, and you will not get this extension on your neck causing it an injury. I hope that this was helpful in giving you an idea about kind of applications of first law of motion, and also forces when they're balanced or not, and how they could affect different objects' motions.